Hi, this is a lesson on the genetic algorithm theory and a step-by-step coding solution to a specific problem. I hope anyone who watched this to the end is totally able to build a GA for any situation. If you don't know anything about search engines or this kind of stuff, I recommend you to watch other videos because this is very straightforward. It's just how genetic algorithms work and how to code them. If you want to skip the theory, you can jump to the coding section. As you can see, the whole process of the GA is based on the theory of evolution of Charles Darwin, where a population of individuals is going to be evaluated by the environment, a temperature, predators, and this kind of stuff. Some of them are going to survive and others are not going to survive. So this means some of them are selected and their genes passed to the next generation by the crossover. After this crossover, children are going to be created and subjected to mutations. This way, a new generation is born and evaluated by the environment again, and some of them are going to survive. Not basically the whole process will happen again and again and again and again until the next few individuals are better fit to the whole environment. An overview of the whole process is presented, where it starts when we generate a random population of individuals. Those individuals are later evaluated using a function called fitness. Then we enter a loop which create a new population. Parents are selected by a method called tournament, and those parents generate children by the crossover and mutation methods. Crossover makes the chromosomes of the chosen parents and after are subjected to a mutation. When this crossover and mutation techniques are over, children are now part of the next population. This whole procedure of generating a new population and evaluating its individuals, it's what is called a generation. So on the beginning of the process, you need to set a max number of generations. So when the last generation is finally completed, the pipeline ends. So that is how the whole process goes. So now we are going to make a in-depth analysis of the function. Before the comprehension of what the functions do, we have to first acknowledge what is a individual. So basically, an individual consists on a chromosome and its fitness score. The chromosome being an array of integers, in this case, and the fitness score being a value. Uh, Most of time, the fitness score means the highest, the best. So it's an arbitrary number which alone means nothing, like 80 doesn't mean anything, but the fitness score explanation was kind of off, but what I was trying to say is that despite fitness score can mean something like accuracy, precision in machine learning, it might just be an indicative of higher the best. And now the concept of a population is very simple. It's the agglomeration of many individuals. So as you can see, we have the yellow, blue and green individuals together and more, which consists on a population. If you remember, the selection is to pass the best genes for the next generations and eliminate the worst genes. In this example, we have 4 individuals that we are only showing the fitness score, which is what the selection is about. We just need the fitness score. So 2 individuals are randomly selected. Let's say the green one and the blue one were selected. Then the worst one is eliminated. From these two, the green has a higher fitness score than the blue, so he is selected. Then another 2 random individuals are selected. In this case, the pink one and yellow were selected. The yellow is higher than the pink one, so yellow won. which means we have two parents. Now we have the crossover, which brings both parents we selected before. If you remember, the green one and the yellow one were the selected individuals. So I brought their chromosomes here, and we are performing the crossover on both. So it all starts choosing a place to partition the chromosome. So where we can partition these chromosomes? We can partition here, 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 and here. I chose this place, simulating a random choice. So the partition always segments the two chromosomes in 4 pieces: the top and bottom of the first chromosome, and the top and the bottom of the second chromosome. So the first child is generated using the top of the parent 1 and the bottom of parent 2, and the second child is made by the top of the parent 2 and the bottom of the parent 1. Which you can see, the first child here has the top in green and the bottom in yellow, and the second child has the top in yellow and the bottom in green. Finally, we have the mutation. As you can see here, each gene is subjected to a chance, in this case 10%, to mutate or not. The only genes that mutated were the third and the last one. As you can see, the old 55 value was replaced for a new random value of 14. And the last one was 35 and was replaced for 22. This is very important because it helps the genetic variability to be present. Imagine that the optimal solution did not exist on the parents of those children. How can they achieve that by the chromosome, if the chromosome just take the parents' values and reorganize them? So the mutation makes this possible. It creates another value completely random. With all those functions in mind, I'm presenting here a problem which consists in finding the highest value of the following expression: b divided by a plus c. A is between 1 and 10, b is between 11 and 20, and c between 21 and 30. So there are 10 options for each variable, and we want to find the optimal solution. In this case, the best solution is a equals to 1, b equals to 20, and c equals to 30. So the expression results in 50. This expression is our fitness function. So the highest this expression results, the best the individual is. Now we have to design our chromosome, which will be an array of length 3, and each of its slots will be filled by a integer on the intervals described on the problem. And as I said before, the fitness function will work like that. Let's say we have a chromosome of 5, 15, and 26. The fitness score of this individual would be 29, because we have b divided by a plus c. In this case, 15 divided by 5 is 3, plus 26, 29. So with all that in mind, we are now going to code. So let's start the coding. As you can see here, I just import those two functions from the random library: choice, which gives a random item from the determined list, and randint, that gives a random integer between two numbers you set. So as you can see here, we will need two classes for this: the individual and genetic algorithm class. So the individual here, there's just one function in the constructor. So we are going to use the individual much as a container for the chromosome, index, and the fitness score. And the toString method is just so that the file we create is easier to read. So we get the index, the chromosome, and the fitness score of the individual. Now the genetic algorithm. As you can see, we have the generate individual, generate population, fitness, population fitness, selection, crossover, mutation, and initialize. Those two are just so we can write on the file easier. So as you can see, generate population and generate individual work together for this generate random population here. Then we have the fitness function that evaluate those individuals. Then we have the population fitness, so we can run that through all the individuals. Then we have the selection here, where we select two parents and return them by tournament. Then we have the crossover, which will get as arguments parent 1 and parent 2, perform the crossover. Then we mutate the children, and then a new population is created. So here on the initialize method is just so we can call every other method. Starting at the constructor here, we have max generation, population size, and mutation rate being passed here on the constructor. So the default will be max generation of 10 and the population size 10. So on the end we have 10 times 10 to a total of 100 iterations of the genetic algorithm. That means we have 100 fitness evaluations. Also, the mutation rate here is, I wrote it like an integer, 10, but in our code I'm going to use it as a percentage. So this 10 represents 10%. If you want 20, would represent 20% too, but I'm sticking with 10. Here, I just define the attributes using those three here, and I create a new attribute that doesn't use anything we passed. It's just a empty individual. If you see here, an empty individual have a chromosome of known and fitness of 0. The best individual will be stored on this variable. Then we have the chromosome shape, which will store the index 0, index 1, and index 2 of the chromosome. If you remember, the first index of the chromosome will be an integer between 1 and 10, the second an integer between 11 and 20, and the third an integer between 21 and 30. So that's exactly what we are doing here. This range function generates a list starting from 1 and ending on 11 minus 1. The same goes for 21 and 31 here. So we end on 10, 20, and 30. So we have three lists of 10 integers. Now we have the generate individual function, which will define a chromosome here as an empty list, and then we append in the right order using the list of index 0 here, which means the first item of the chromosome. So this choice is going to return a random value of the list contained on the index 0 of this variable. So the choice is going to return, for example, the number 2, the number 10, the number 3. The same goes for those other two lines here, but the list's gonna change. As you can see, index 1 and index 2. Finally, we return the created individual using the chromosome and the index we got from the argument here. Now we are going to use the generate individual a number of times equals to the population size. So by default this is 10. So this append is running 10 times. We are passing the index of the loop here. So So we create 10 new individuals generated randomly by this choice function. The combination of those two methods are the first step here. So using both generate population and generate individual, we can finally generate a random population. Now we have to evaluate the individuals created, as you can see here. So we are defining A, B, and C. A is the index 0 of the chromosome, B is the index 1 of the chromosome, and C is the index 2 of the chromosome. This is the fitness function, as we want to optimize this expression. And as I said before, we want to store the best individual here. So the best individual is the individual who has the highest fitness score. So we compare the fitness of the best individual and check if it is less than the current fitness here. If the current fitness here is greater than the best individual fitness, now the current individual is the best individual. Then we return the fitness here. So population fitness here, just as the generate population calls the generate individual 10 times, population fitness calls the fitness function 10 times too, the length of the population. It's worth noticing that this population is not a list of lists, it's a list of individuals. So that means it's a list of this class individual here, which means each index of this list has a chromosome, an index, and a fitness score. Now we have evaluated all the individuals, then we have to select the parameters by tournament. So I'm just writing selection here. First we define parents as an empty array, then create a loop that iterates twice. This means 2 tournaments are going to be done here. The first tournament, as you can see, we create the contestant number 1 and contestant number 2. Both of them are a random individual from this list of individuals, which is the population argument we are going to pass, the current population we want to select parents from. So we choose a random here and another random here. Then we do the tournament, which is very simple, as you can see, 3 lines. First we define a parent and say it's equal to the contestant number 1, but if the contestant number 2 fitness is greater than the contestant number 1 fitness, the parent switches to the value of the contestant number 2. Then, after these lines are ran, the parent here is the best contestant, so we can append this parent to the parents list. As this iterates twice, at the end of this for, we have the parent on the index 0 and the parent on the index 1. So after we finish the select parents, we are going to the crossover and mutation. So the crossover takes the parent 1 and parent 2 arguments. The index here, as it appears many times, it's not necessary, but I like to use it, so the file we are going to create is more readable, but you can skip this index if you want. First, we have to choose the partition of a chromosome. As you can see here, we chose this partition. As you can see here, randint, a random integer between 1 and the length of the chromosome minus 1. Here we are sectionating the chromosomes of parent 1 and parent 2. So the parent 1 chromosome will start at the beginning and goes all the way to the partition. It doesn't quite get the partition, so the index of the first child would go index 0, index 1, index 2, and index 3. So the partition is 4 and it goes all the way to the index 3. So it's always 1 less than the number of the partition. As we don't quite get the index equals to the partition on the first chromosome, we start the parent 2 at the partition. Now this makes the children chromosomes be the same length as the parent one, and we go all the way to the end. This means it goes to the end. The same way this means it starts at the beginning. So the difference between chromosome 1 and chromosome 2 is that chromosome 1 starts at parent 1 and chromosome 2 starts at parent 2. Both end inverted too, so parent 2 is the bottom of the chromosome 1 and parent 1 is the bottom of the chromosome 2. As you can see, child 1 and child 2, we just use the chromosomes we created above and pass the index here. Then we return both children. Now the mutation. We define a new chromosome here and start it as the same as the child chromosome we get from the argument. And we create a loop that iterates through every single gene of the chromosome. So this if statement here simulates a percentage chance. We will choose a random integer from 1 to 100. So we have 100 possibilities for this number. But we are checking if it less than or equals to the mutation rate, which is 10. So for this number be less than or equals to 10, the number can be 1, 2, 3 to 10. So we have 10 possibilities where this is going to return true, and we have 90 possibilities where it's returning false. So this means 10% chance of mutating. The mutation is basically another random choice from the possibilities you can find on the specific index of the chromosome. So if the index 1 of the chromosome mutate, we are going only choose values that can be on that index of the chromosome. As you can see, if the index 1 mutates, we don't want to use this list. We want to use this one. And we specify this by using the same index as the chromosome. Then we say the child chromosome is equals to the new chromosome. We return none here because we are modifying the child chromosome. We are not returning. So this is the mutation. If you see here, all the named methods have already been explained. We are going to do all of that on the initialize method. As you can see, first we have to generate the random population. So we define population and we call the generate population method, and it's called generation 0. Then we have to evaluate its individuals, so we call population fitness, and we pass the population we just created so that the fitness values can be placed at each individual. Then we write this generation to a file. Then we are going to loop for every generation until we reach the max generation. We start here at index 1 because we have the generation index 0 here, so we don't want to repeat that. So we are finishing on generation number 9. Then we have to create a new population that is represented here, so that when we append new children, we don't stack them on the old population. So further append the generated children. We are making another loop where it grows from 0 to the population size, which would be 9 in this case. So 0 to 9, making a total of 10, but we are going 2 by 2. This step 2 means that this index here is going to be 0. Let me write. The index here will get the values 0, 2, 4, 6, and 8. So we are skipping the odd numbers, because as we create 2 children at a time, if we didn't have the step 2 here, we would double the size of the population. So here we get the 2 parents from the selection method. Then we use those 2 parents that won the tournament to make the crossover, and we pass the index. This index here will be passed to here, So we have 0 and 1. Then the index is 2, so 2 and 3. This way we complete all the values between 0 and 9. Then, when both children are generated by the crossover, we are now mutating them, so we call the mutation method and pass the child 1, and we call the mutation method again and pass the child 2. Next, we append both children to the new population in the right order. So, after all this loop end, we have a new population fully developed here. We have to evaluate it. So, as you can see, a new population is generated, and the next step is to evaluate its individuals. So we are evaluating the new population. Then we are writing this generation here, and we say that the old population is now equals to the new population. So further, when it comes back to the loop, the new population will be restarted, and we can now select from the old new population. And then we write the best individual for each generation. That means on the 9th generation, this will write the best overall individual. An interesting thing to notice is that this for is represented by this statement here, max generation reached, as you can see, max generation. And this other loop represents this population size reached, which will select parents and reproduce them. As you can see, select and reproduce them. Finally, we have the right generation. This is just the code so we can write everything in a file, so the results are easier to read. Here I just create the file called GA results and write nothing. I'm just creating the file. And then for each generation, I call this function. I will pass the population as argument and the index of the generation. So I write generation and its index, and I iterate through every individual inside this population. And I use the toString method, so we can use the string right here. The last method we are going to use is the writeBest. Again, I open the same file and I write the best individual we have so far. Finally, with everything already created, we just create this object and we use the initialize method. As you can see, the initialize method here calls literally all the functions we need, so we just have to call that. I'm gonna run it and show the file I got. Oh, here it is. As you can see, generation 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The important thing to notice is that the highest fitness we got here is 38 and the others are really low. And in the last generation, the highest is 49, which is almost 50. We just lack the 30 here, which probably we didn't even find. So our code review ended here. If you want to make an analysis of the results or run this code by yourself, I'm going to put the link in the description. So I hope it was useful.